We may often temporarily ignore the randomness and uncertainty of the history. As Democritus said, everything existing in the universe is the fruit of chance and necessity. So, there should be some clues behind the advent of Centre Pompidou. Obviously, the advent of Centre Pompidou cannot be ascribed to a single event or reason. We can probably classify the reason to three aspects: the history, the architectural trend, and the art and technology. If we split the timeline into two parts, before the 20th century, both the society and the architectural industry experienced tide and revolution over and over again. Since the beginning of the 20th century, this process of revolution has become even more frequent. Although there was a great economic recession after the Second World War, it soon recovered because of the Marshall Plan. Along with the recovery, leftist gradually became the mainstream ideology of the French society. May 68 finally broke out, which directly made Charles de Gaulle stepping down. After May 68, the new government urgently needed to unite the people from all the social background, so a cultural and art center was planned to be built and named after de Gaulle's successor, Georges Pompidou. In the architectural, industry, and art trend aspects, together with some events, May 68, for example, many great avant-garde architects like Le Corbusier, Buckminster Fuller, Cedric Price, and Archigram remarkably changed the way of architectural design. The development of the structure and material technology reshaped the way of architecture as well. All of these events lead to the final result of Centre Pompidou, and it certified that architecture is always closely related to the social and technological development. Centre Pompidou was a great response to that era. What can we expect for architectural response to our era? Perhaps a transformable building is the one that adjusts to that ideology. Next is about the research we did for understanding transformative. First of all, we consider that general transformation can be defined in different domains, such as biology and medicine, computing, mathematics, physics and chemistry, etc. The transformation research that we focus on is from a branch of mathematics, geometric transformation. More specifically, the geometric transformation can be categorized in biomimetic, rigid, deformable, and flexible transformation. Although this kind of classification methods are systematic and precise, it is difficult for us to push forward our design process. So we try to introduce the force-based definition from physics to make them efficient and easy to be extracted and used. First, we prepare to use physics conception. They are divided into fundamental, non-fundamental, chemical, and underlying forces, as well as rotation and torque. Chemical and fundamental forces could be currently uncontrollable for us. So finally, we focused on non-fundamental forces, underlying forces, and rotation torque. The research of non-fundamental force is based on an umbrella system prototype, in which the sidebar moves correspondingly with the center bar moves vertically. And the research of underlying forces is based on a transformation system controlled by magnetic balls. Because it is too soft and difficult to control, we temporarily shift our focus on the cube folding system, which is based on rotation and torque.
Initial research. First of all, we define a cube which can be unfolded into 6 square pyramids, and they connected each other with 5 hinges. They can be folded into a cube with 1 to 3 faces standing out, or, in the most extreme cases, folded into a dodecahedron. As shown in the video, there are 4 out of 11 ways to unfold a cube. Then we try to research the combination and interlocking of multiple cubes. Basically, in order to interlock with each other, one face of the cube has to be unfolded to generate an angular shape, and it can plug in another void shape, which was generated by unfolding a face from the cube as well. And the latter cube can also plug in the former one by rotating the hinge. Additionally, dodecahedrons can be combined as well. We also analyzed the possible shapes of all 11 types of folding process. But we found some limitations of our research method. The first thing is that we ignored many possible forms because we constrained the final shapes by just identifying the numbers of the faces standing out of the cube. Second, the combination of each unit should not be constrained by an initial condition based on the cubes, which could reduce many possibilities of the combination. In order to find out the reasons of the problems above, we proceed to the next phase of our study.
The third chapter of our presentation is further research about the definition of meaningful and possible forms, the database of the forms, and computational tryouts in Unity 3D engine. In order to solve the problems of previous research and make our research more controllable and feasible, we define some basic principles to categorize all the possible forms when folding the square pyramids. Basic principles. The hinge connection plays the main role in transformation. It is the torque of hinge that triggers all the possible forms. There are only 3 ways of rotation triggered by hinges. We define it a positive 90-degree rotation if the cusp of a pyramid goes towards the cusp of another one. In the other way around, we define it a negative 90-degree or negative 180-degree rotation. We assume that transformation happens in an ideal and theoretical environment, which means that no extra force exists except the twisting force of hinges. Then we begin to categorize all the possible forms during transformation. In order to make our research more systematic, we number the hinges of all the 11 unfolding ways, from 1 to 5 in each of them, and all the rotation will follow this order. Also, we introduce colors to show the valence of each pyramid. In our color system, black represents the terminal pyramids. Yellow means that it has only one adjacent terminal pyramid. Red one means it is connected with 2 terminal pyramids. Green one means it connects with 3 terminal pyramids. Gray represents the ones that have no terminal adjacent. The color system describes the relationship and valence, so even the same folded form could contain different meanings because the valences of pyramids are different. This color identification may have great potential in our further research.
The states of transformation. In general, all the possible forms generated by the transformation process can be defined in 3 states: the initial state, the procedural state, and the stationary state. All the states can be described as the total number of hinges that experience rotation, and each hinge can be rotated once only. The initial state means that no hinge has been rotated. The procedural state means that at least one hinge has been rotated, and the maximum number of hinges that have been rotated is 4. The stationary state means that all the 5 hinges have been rotated respectively. For procedural state, it can be subdivided into regular and freeform. It is easy to understand the regular procedural state. In this state, by rotating positive 90 degrees or negative 90 degrees, or negative 180 degrees. All the faces are perfectly attached, either as triangular faces or square faces. In the free-form procedure state, there are meaningful one and meaningless one. The meaningful free-form procedure state describes forms that are relatively regular, which are more likely to be used as spaces. Stationary state. Similarly, stationary state can also be subdivided into regular and free-form. We consider that regular stationary state as our final form state that could be based on to further our research. That is to say, each final form is generated by 5 steps of folding in a specific sequence and cannot be folded anymore. Based on the most systematic and feasible principle, we define a way by using the paths and the routes to show sequences from initial state to the final regular stationary state. We choose initial state of type H as an example. We know that any final form experiences 5 steps of hinge rotation. For each hinge, there are 2 directions to go, as each one can only rotate once, either in positive 90 degrees to make 2 triangular faces attached, shown in a red route, or in negative 180 degrees to make 2 square faces attached, shown in blue route. Additionally, there's an exceptional route shown in yellow, and we will explain that later. The game begins. In step 1, we follow the red route to rotate the hinge 1 by positive 90 degrees. In step 2, we follow the blue route, which means the hinge 2 is rotated by negative 180 degrees. In step 3, we also follow the red route. Hinge 3 is rotated by positive 90 degrees. In step 4, blue route again, and step 5, red route again. So far, we have successfully created a final form. It is number 8 of all the regular final shapes, and it can also be named as HRBRBR, which represents the unique route of the generative process. Now we're back to the initial state and try to follow another route, which is quite special. In step 1, we follow the blue route by rotating hinge 1 with negative 180 degrees. Then in step 2, we would like to follow the blue route, but we found it impossible to rotate the hinge 2 by negative degrees because the contact surface of a triangular face and a square face cannot be considered as our predefined regular procedure state. But if we skip hinge 2 and directly rotate hinge 3 by negative 180 degrees, shown as the yellow route. After that, we found that hinge 2 could be rotated by negative 90 degrees to proceed into the next step. Now we come to the step 4. Red route is our only choice. Step 5, just the same as step 4. Now we get a final form, H15, which can also be coded as HBBYRR. As you can see, for the initial state of type H, there are 15 regular stationary states in total. If we go through all the routes from 11 types of initial states, we can end up in 181 regular stationary states, 20 in type K, which is the most, and 13 in type F, which is the least. Because the initial states and folding orders are different, all the 181 types of regular stationary states are unique, even if some of them are geometrically the same. In order to evaluate the feature of each shape and count the number of geometrically different shapes, we introduce the value which can intuitively describe a shape in 3 aspects. P stands for projection, which means the maximum projection of the shape. It is the total number of the projected triangles minus 4. So the p-value of the cube is 0. I stands for intervention. It is basically the number of the pyramid's cusps that's standing out in the final state. The I value could describe the chances of the shape that insert to another void. Letter A stands for absorptivity. It is the number of the voids that another pyramid could insert and interlock. We finally categorize all the 181 regular stationary states into 13 different PIA values. We also noted that shapes with the same PIA value are topologically the same, even though they are geometrically different. We are also interested in finding out all the geometrically unique shapes among the 181 regular stationary states. To prevent any careless omission, we translate the root diagrams into an Excel sheet, and we finally sort out 43 geometrically unique shapes in total.
Each stationary state has an exclusive designation name and code which describes the rotation of hinges. Projection, involvement, and absorption are the underlying properties, and PIA values stored for them. Regardless of hierarchies and hinges, 181 stationary states are divided into 43 final states, and we translated designation code into Unity 3D system in order to digitize them. We use this as our setting up database. Basically, there are 4 levels of hierarchies showing from darkest blue to lightest blue. The darkest blue pyramids are the parent level, and the lighter ones are first level child, so on and so forth. When folding begins, the movement of pyramids from lower hierarchies are always driven by the folding of higher hierarchies. In Unity 3D, we called it a positive 90-degree rotation of hinges using kpress Q, W, E, R, T, following the hinge sequence 1 to 5 as mentioned before, and a negative 90-degree rotation using kpress A, S, D, F, G. Taking the shape K10 as an example, in our previous encoded system, it is encoded as K dot RBRBR, but in Unity 3D for keypress, it becomes K dot QSSEFFT. Let's look at another example, K17. It is K dot BRBBY in previous system, and K dot AAWDDGGF in Unity 3D. Our proposal for the next phase is to explore how the units interact and connect with each other, and set up a series of principles that guide all behaviors based on an appropriate criteria.